Welcome to my channel. In this video, we are going to talk about the solver settings. In the previous video, whenever we have created model and executed, we were never looking into the solver settings and it got executed with the default settings. So let's have a look. What is the execution result that we see as a default? I am going to add one constant, an add block, one unit delay I need, one scope, and one display. Let's connect the signals. Then this add will go to scope, also to display. What I want from add output, I want to connect to the unit delay. So I will flip this first. So I'll go into the rotate and flip block so that my input will be on the right side. So I can connect to this add output, and output will be on the left side so that I can connect to the input of add. Execution will go like initial value will be 0 from unit delay, 0 plus 1. So first time we should get 1 value, then 1 will be again sent back to add block, then plus 1, 2, 3, 4, like that. Let's execute this, and we are getting 51 values, the last value. Let's see scope, how it is incrementing. So 1, 2, 3 and till 51. So 50 iterations we are getting within a time of t equal to 10. This is the stop time, that is a 10 second. Okay. Now let's go to the solver setting. Let's see what are the default settings we had. In the simulation time, we have start time as 0, stop time as a 10 seconds. So these are in the second as a unit. In the solver selection, we have variable step by default and solver automatic solver selection. What are the other options that we have in the solver selection? Variable step and the fixed step. So first we'll understand the fixed step. In a fixed step, what will happen? You will define one step time that we call as a fundamental step size. Let me expand this. And this is the fixed step size which we call as a fundamental sample time. So this time will be after that much time, every iteration will get executed. So if I give this as a one value, so 1 second, after each 1 second the model will get re-executed. So considering 10, it will execute for 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we will get the 10 executions. So let's try this, save it as a OK and then execute it again. So we got 11 because we are starting from 1 and the 10 iterations, so it went till 11, right? So in case of fixed step, I am defining by myself. There is an option where my solver can also decide by themselves. So if I go here fixed step, and if I don't select auto here as it was written earlier, my solver will decide how much fixed step size I should give. But we generally go with a discrete non-continuous state. So where I'm particularly giving the value and I want to simulate my model with the same iteration every time. Then what could be the difference of this variable step? Let's go and understand. I'm going to create one situation here. So we have one fixed step. Second, we have the variable step. In a fixed step, my step time will be constant all the time. Step time constant throughout the model iteration all the time, right? In a variable step, it will be varying. So varying as in the beginning, my step time will be higher. At the beginning, step time higher, and at the end step time get reduced. Why is that? Because at the beginning my simulation result is changing slowly. So if my simulation is result is changing slowly, to reduce the computational cost, I can make the step size higher, right? If my value is not changing much, then why should I do so much computation with a small change of time? I can keep the bigger. However, in case of ending, now when I'm coming to the saturation or the optimization state, where my to get that accuracy, I have to do this too many iterations. So during that time, I will reduce my step time, and then I will try to get the accuracy. So that's what happened in the end. If you have seen some gradient descent kind of optimization method, non-linear optimization, so this is my minimum point and your iteration starts from here. So as per the gradient descent, you take bigger jumps to reach this point. At the beginning you take bigger jumps, then get reduce and reduce, and then somewhere when you close to this you start getting very doing very small steps. So this is my, because here to get that accuracy of finding any minima or any optimization method, when you go close to the accuracy result or the say end of the simulation, you have to iterate the small step size. And in the beginning, because your change is very slow, then to reduce the computational cost we make the step time higher. Let's have one example. I'm giving one guy is jumping and your job is to count. So your breathe time between the jumps is your step size. Okay. And the time between his jumps is your simulation accuracy. Time between jumps is simulation accuracy. Okay. So at the beginning, let's consider that variable step we are imagining as a solver. So at the beginning, he's jumping slowly. So you have good time to count it. So when the jump is very slow, then you can achieve the simulation accuracy during with this bigger step size. So if I say jump like 1, 2, 3, 4. So if this much space I am giving between my two counts, the breathe time is higher. So step size is higher at the beginning, right? Now, when it close to the end, while the simulation is existing, then he's jumping fast now. So closing to, like, before he finishes all the jumps, he wants to close, increase some counts of the jumping. So that's why at the end he is just doing faster jumps. So then my count should be faster. So I will say 4, 6, 5, 7, 8, 9, 10. Right. So here my breath time is low. So to achieve that simulation accuracy, so achieve as in to count that all the jumps that he has taken very fast, to achieve that simulation accuracy, because the time between jump is the same, I have to decrease my breathe time. So that is, I have to decrease my step time so that I can achieve that one. So you understood with this example, with like in general, you just imagine this problem, same approach, and you will feel it like when the jump is very slow, you had time to count that. That is the higher step size. And when jump become faster, you had no time to count it, so you have to reduce your breathe time. That is, you are reducing your step size. Reason is, at the end you are achieving that simulation accuracy because the jumps are very fast now. So hope you understand these two differences with very simple examples. Now coming back to model, what else we have? So this is our difference between the solver selection. Now the solvers types. So we have different type of solver here which are applicable for both fixed step and the variable step. This ODE is a very general term, ordinary differential equation. So, and these are the different algorithms which you can read it into the any optimization books. These are based on the stiffness. So stiffness is basically how many differential operation you have in your equation. Now we will not go through one by one, but I will share the document which you can help you out. So one document is ODE 45. You can go through this document, and at the bottom when you will go here, you will see the other solvers also. So here ODE 23, 78, 89, 113. And the another document which you should refer is the explore variable step solver with the stiff model. So stiffness that we talk about, which defines how much the derivative operation you have into your model, right? So here's the one comparison of these solvers. Which solver is useful for which purpose? So if you know your problem doesn't have any derivative operations, then you can go with a non-strip ODE45. But this is having medium accuracy. So for non-strip, low to high is somewhere here, but it's a fluctuating depending upon your problem. And here also they have given when to use. So read this and consider your problem, compare which type of problem it belongs to, and then you can decide your solver, particularly when you want to design your step time based on the solver definitions. Otherwise, if you want to design by yourself, you can simply go with a fixed step and then a discrete on the other side for the solver, discrete non-continuous state. Okay, so this is all which we want to talk about, and hope you understood this differences of the solver type and the solver settings. Thank you so much for watching. See you in the next video.